So we'll look at worksheet number 13. So homework last night, specifically questions 3 and 4. Question 3 says, calculate the initial acceleration of a 50-gram, 20-centimeter long wire. I'm going to circle these because we want to convert. Carries a current of 6.6 amps and is exposed to a magnetic field of 0.50 Tesla. What do you almost always do in Physics 30 when you're looking for the acceleration? What needs to be with you? Yes, may the force be with you. And once it is, then we're just going to say A is equal to F over amp. So let's get the force first. So let's say the force on this wire is ILB. If you're looking for the magnetic force on just a charge, it's QVB, but on a wire, it's ILB. I is 0.600 amps. L, the length of the wire in the magnetic field, is 0.20 meters. We're going to say 20 centimeters divided by 100 gives me 0.20. Times B, 0.50. Okay, multiply those together, and we're going to get a value of 0.060 newtons. All right, there's my force. Now that the force is with you, let's do our little Jedi thing and get the acceleration. A is equal to F over m. The force is 0.060 newtons, and the mass here of this wire is 0.050 kilograms. That's 50 grams divided by 1,000, giving me 0.05 kilograms. We do the math there, it works out to be 1.2 meters per second squared. All right, let's take a look at question number 4 as well. This one says a 15-centimeter long wire carrying a current of 0.2 amps. Here's an external magnetic field. It's suspended. It's suspended. All right, that's the key word here. If it's suspended, then we know it's in a state of equilibrium. And if it's in a state of equilibrium, then we must have forces that balance. Which two forces balance here? The only thing it mentions is the magnetic force, right? The other force must be gravity. So let's set Fm equal to Fg. Now, here's what some people did when they solved this question. I watched you yesterday, some of you, as you solved the question this way. You said F is equal to ILB to find the magnetic force. You said I is 0.20 amps. L is 0.15 because we got to convert that to meters. And the magnetic field is 0.300 Tesla. That gives us 0.009 newtons. And then, well, let's set that equal to the force of gravity. If they balance, and they must balance because it's in equilibrium, then the magnetic force will be equal to the gravitational force, and I can just sub in that value for the magnetic force in here. Divide it by 9.81. That gives me a value here for the mass of 9.17 times 10 to the negative 4 kilograms. Now, how many people did it that way? How many people calculated the magnetic force and then set it equal to the gravitational force? How many people did this? How many people right off the top said the magnetic force is equal to gravity, and therefore ILB is equal to m times g? How many people did it that way? That's the way that I would prefer to do this. The first way is absolutely correct, but I'd prefer the blue way here. Here's why. In this question, to be honest, it doesn't make any difference in this question. But sometimes when you set two things equal to each other like this, sometimes something will cancel. Sometimes it appears on both sides. Let's say you were doing a magnetic force and you had to set that equal to the electric force. And you're trying to solve for the magnetic force first to sub in here, but you didn't know what the charge was. Well, then you couldn't solve for the magnetic force if you don't know what the charge is, right? But if you set the magnetic force equal to the electric force right off the top, like we did here with magnetic and gravity, then the charge actually ends up canceling, and we can still solve the problem. Does that make sense? So the potential value of setting them equal to each other right off the top is that sometime you might need to cancel something, and you're going to recognize that. When you do it separately, like most of you guys did, that option to cancel isn't going to be there, which we didn't need in this case, but sometimes we might because of missing data.